Welcome and good morning. Welcome to our talk about what happens in Windows 7 stays in Windows 7. We're going to talk about vulnerabilities today and how to find them and identify them. As our moderator already introduced us, my name is Marion Marschalek, and my friend here is Moti. I work as a malware analyst, and in my spare time I like to do reverse engineering, as mentioned before. The challenge was particularly hard, as we all know that there's so many females in that business that the challenge was like highly overran by participants. Now, with this project that we present today, I entered kind of a new field for me, but I think Moti is more of a specialist on that.
Basically, I'm a security researcher, but I work for Parsing. In my spare time, I'm a day trader. And that's it, basically.
Right, and today we have a long list of stuff that we want to tell you, but we're actually going to try to speak fast because I know everyone's hungry. We're going to talk about vulnerabilities, more particularly about how to find vulnerabilities in standard software. And we're going to present an approach that we came up with to automatically spot vulnerabilities in binaries. More particularly, we focused on Windows binaries, especially Windows 7. And we're going to show you a solution for our approach, how you can find vulnerabilities in Windows 7 libraries by diffing them with Windows 8 libraries. This as a whole concept is not that new, as some might know. What is new about our approach is that we tried to automate it and make it fast and easy to use. We're going to show you a demo about how to use our tool, and finally show us our results, the potential vulnerabilities that we found with our tool. Introduction. Why would we want to find vulnerabilities in software? Some might have heard that there's a kind of shady business being established around vulnerabilities. There's people who want to find them, there's people who want to buy them, there's people who want to sell them, there's people who want to exploit them. So we have various people being interested in vulnerabilities and a big group of people actually working on that business. And, well, we're going to try to present a solution for these people to make their work faster. What is this whole business about vulnerabilities? I put a quote here on that slide from a very famous security researcher, also named Chuck Norris. More particularly, his name is Bruce Schneier, who wrote this nice definition of vulnerabilities and how they are being created basically either by misconception or bad programming, bugs in programs, and that they can actually be used to attack systems. I'm pretty sure everyone in here is familiar with the term exploit. Maybe how to use exploits to actually exploit dedicated systems and hack these systems, intrude networks, and eventually maybe infect systems or steal information. And as we all know, there's a lot of bugs out there. If you follow the news, there's more and more vulnerabilities being discovered and exploited and detected and maybe even patched. But in fact, there's a lot of them still unpatched out there. More particularly, no patches available for specific vulnerabilities or systems with vulnerabilities which would actually already have available patches but are not patched in the end and so stay vulnerable on the internet. Now, for people who don't know who Chuck Norris is, we found a very good portrait of him on the interwebs. I particularly like this one. I grabbed it from a website where you can actually buy T-shirts with printed Bruce Schneier effects. Not to make marketing, but I thought that's a pretty cool idea. And someone said he even designed those shirts himself, which I thought pretty awesome. All right, how to find vulnerabilities. This is actually a pretty decent summary saying, like, almost not everything that you can do to find vulnerabilities, just the most important facts. A feasible way would be application penetration testing, also including fuzzing, where you just try to morph input for specific interfaces of an application and try to get awkward behavior. We try to find crashes, actually. So if an application crashes, it's always a good hint that there might be a bug in there that you could eventually maybe exploit. Another approach would be reverse engineering, which is kind of tedious if you ever try to reverse engineer a binary. It takes a long time, and it's hard to find an anomaly in there, as usually reverse engineers try to find functionality and not functionality that shouldn't happen in a binary. Also, a feasible approach is source code review, very frequently done by dedicated companies offering this as a security service, to review the source code of a standard application to find bugs in there and to allow the vendor of the software to fix them. In case of open source software, this is also very possibly being used by hackers to find vulnerabilities in open source software and eventually hack that software. Or we also listed some ideas how you could be more advanced on vulnerability search, which I thought pretty creative ideas to simply track software bugs that are being reported that might get patched at some point or stay unpatched for a long time because the vendor just doesn't care. But still people publish information about bugs. So if there's eventually an exploit being written for a known software bug that either never gets a patch or is not patched on the end system, this stays an open vulnerability that could eventually be exploited. Also, a nice approach would be to introduce bugs in software. As you might know that there's some money you could eventually make with a vulnerability, it might be useful to just simply bribe the programmer to introduce bugs in software that you could eventually exploit later and gain more money than you actually paid the programmer to introduce the bug. And the approach that we concentrated on for our research was reversing security patches. Like, as you know, if there's a vulnerability found and a patch written for it, sometimes these patches themselves are vulnerable, or even worse, not being applied to every system that is out there, which happens very frequently. So for our research, we concentrated on missing security patches on Windows 7 systems that got maybe applied to Windows 8 already, but didn't reach the Windows 7 platform. We didn't directly reverse engineer security patches themselves, but concentrated on the library to diff for missing patches that were present in the end binary in Windows 8, but not on Windows 7. And to get back to the bugs. Who's interested in finding bugs? Well, as I mentioned before, there's a broad range of people who actually want to find software bugs. Most of all, and initially, it were hackers who just wanted to play with binaries and try to break stuff, break systems, for not so much financial motivations, but just for fun. Then there are software companies who actually want to find vulnerabilities, mostly in their own products, to be able to patch them and not have their end user being vulnerable to attacks by hackers, for example. We have a third group on that slide that I'm not totally sure if the term actually is the correct one to apply, which would be criminals who use vulnerabilities or available exploits to attack businesses or governments, to exfiltrate data or spy on the dedicated victim, which, as we all might have heard on the media today, is not necessarily only criminals spying on businesses, but sometimes businesses spying on governments, or governments spying on criminals, or businesses spying on private persons, or private persons spying on governments. Or some people who might have followed the media might have noticed that there's like a broad spectrum of interests in hacking motivations. All right, and as I'm talking about it, the fourth group we listed on there would be governments, who, well, we don't actually officially really know what they're doing with it, but there's a guy out there, I believe he's named Edward Snowden. He knows a bit more than we do about what governments actually do with vulnerabilities. I'm not sure if this is openly available information. And the last point on it would be media. I added them because I really like the media very much and what they actually very creatively write about security issues that are out there in the field. Yeah, and they're also really interested in vulnerabilities, I believe, because every time one is discovered, there's a big report about it from several different sites. And finally, why are all these people so interested in it? Well, they're not all doing it for fun, maybe besides the hacker, but most of them are interested in some sort of revenue because, as you heard, everyone got this dedicated interest in vulnerabilities. And there's actually a market evolving where pretty huge sums of money actually change owner every once in a while, followed by a vulnerability. Because usually, with these vulnerabilities, you can make even more money later on. So this is most probably the most driving power behind the whole vulnerability research field, the money.
Okay. So let's say you found a zero-day vulnerability and you want to sell it. In the other slide, you saw that basically this is the prices you can get. You can get these prices and even more. But it's not so simple as it looks like. If you are just a developer and you don't have connection with no one, and you will try to Google and figure out where to sell it, you're going to end up with a website like this, ZDI. They will buy the zero-day from you. Even if it's a good one, they're not going to pay you much money. You may get 10K max. And so what you're going to do if you want to get much more money? The problem is that the people that are willing to pay the big money want to stay anonymous. They don't want to know they buy it. And usually the developer don't want to know that he sells to the black market. So must be a situation to connect between each other. So this is where a broker comes to the business. The broker is actually have a very good relationship with the clients. Clients are usually big guys, government, organizations that work with the government. So they trust this guy. The developer doesn't have so much deep information with the broker, but it's his best chance to get the big money. So he trusts and gives the broker a trust. So basically, the broker gets the zero-day from the developer. The developer gives fully trust. The developer didn't get paid anything. He gave everything he had to the broker. The broker transfer the information to the client, verify that everything as requested, and then the payment is started. There's one issue left, it's the money issue. The client wants to pay $200,000, $500,000. He has the money to pay it, but he wants to make sure it's not going to get patched after a day or two, or at least it's exclusive. So usually, they pay in chunks. They said, let's say, every month, you get 50K if it's not patched. So basically, that day basically says, OK, we want it for 6 months. If it's not patched, you get all the money. Every month, you get a little. So the developer is happy. The broker is happy because he gets percent from the sale, usually 10, 15%. And the client is happy because he got what he wanted, the 0 days. And usually, the clients use it immediately. They don't waste time because basically they buy on demand. So what actually happened when this 0 day go to the black market? Basically, it's been used. And every time, usually 90% of the time, when you see this kind of news, it's because one of the black market bought it and used it to hack the system. And eventually, after a period of time, it gets discovered. So this is a perfect case of an office that was used a year, sometimes 2 years, to exploit websites, and eventually it gets out. So you can be sure that there is 0 days out there that actually for years already in the public, but not yet discovered. So this is basically a little how this system works.
All right, so now I understand why people are interested in vulnerabilities. We actually tried to optimize these interests in automating our approach to find vulnerabilities faster. Like, why would we want to be faster? Like, as we're hackers, we could break more. As we're in the grayscale, we could make more money. As we might be involved with governments, we can, well, I can't tell you. And just in case we would work with the media, which we don't, we could write about more vulnerabilities. So we came up with an approach that we believe is pretty awesome, pretty simple, really scarily simple, and faster than actually searching vulnerabilities by hand. So what we actually did was different versions of Windows libraries to spot missing patches. Here on these slides, you can see a simple example that we found by hand searching the Quartz DLL, which is involved with sound processing, I believe, which for sure, as it is involved with processing, is going to accept data at some point and produce some output at some point. And this is actually exactly the library type that we want to find, something that accepts input from somewhere and processes it at some point. So what we can spot in there is functions that process the user input. So we could maybe tweak the input values that specific vulnerable functions would handle to eventually cause, for example, an integer overflow or a buffer overflow or integer underflow or whatever modification that could allow us to corrupt memory inside of this function. So here we have the Quartz DLL where we spotted by searching it with either pro a missing safe function. We define safe function as functions that allow to check input values if they actually fit a given size, that they shouldn't be bigger or smaller than this given size. So in the first example, you see the Windows 7 version where memory is allocated in this last call down there, and the size of memory that's going to be allocated is received by the function through the CL, through ECX basically. So if you follow this assembly code there, you can see that EX is not modifiable, never, but eventually, if you could manage to modify ECX, you could maybe get EAX to have a size, or to indicate a size that could be too big for the buffer that's going to be allocated. On the second side, you see the Windows 8 version, where ulong mod is used to actually check the size of the buffer size that is going to be allocated, which assures that this size is not going to be bigger than a specific value. It should not overrun. So how did we find this? A very simple idea, opening up either pro and doing a string search for this given function that we wanted to spot. So we started our either pros and counted simply the functions that we found in libraries, and we saw there's a difference. So we counted in Windows 8, we have 46 appearances of one and only one always equal safe function, and on the Windows 7 side, we found 44 examples of this, which told us that there were 2 missing on the Windows 7 side. I have to say, just because one of these safe functions is missing, or several of these are missing, doesn't indicate that there has to be a vulnerability, but it is definitely a good hint that there is some security missing on the side where the count is lower. So with this simple idea, we went on and spotting the function in the library where on the Windows 8 side, the safe function was applied, and on the Windows 7 side, the function was not present. We managed to find the specific function that would actually eventually provide the vulnerability. So for an idea of automation, we concentrated on these safe functions, which are actually pretty simple and funnily easy, summed up in 2 header files, like 2 libraries that provide the safe functions for Windows, which is intsafe and stringsafe. These definitions provided us with 130 signatures that would indicate safe functions and binaries, which would care about type conversions, secure mathematical functions like multiplications or divisions, and buffer bound checks on strings for memory allocation, for example. So concentrating on this set of signatures, we collected 130, where I provided some examples here of mathematical functions, for example, who provide secure safe functions for additions or multiplications, and provide functions to check buffer sizes for string allocations. So given these functions, we had the text representation from the header files and would do nothing else than try to get a text representation of the libraries that we are searching, and actually search for the given signatures in these libraries. Then simple, just diff the number of counts that we found of the given safe functions. So this is our approach. The whole way from the Windows library to the diffing and checking for the vulnerabilities is pretty much automated in our system. So we take the library and decompile it with either Pro and the Hexrace plugin and parse this decompiled version of the library into a database. So we have all the signature hits of these safe functions in the libraries in a database, and can afterwards just simply diff it with, well, simple select statements on a database, which is like the most easiest approach ever. So afterwards, we have a diffing of the libraries and just see where the counts differ, so where we have more appearances of a safe function and where eventually in which function we could find a missing safe function. Right, so here's the solution that we finally implemented. I know this graphic is very, very beautiful because I designed it myself. This basically shows the whole process of the diffing that we produce. We have the libraries on the left top corner and use either Pro, actually two tools that we produced ourselves to decompile them to C files. So basically for some very short time I had all the source code of Windows 7 and Windows 8 libraries lying around on my computer, which was a pretty good feeling. Then we did nothing simpler than parsing these files, like going through the files and searching for the safe functions that we defined before and put them into a database. It's just simply the name of the function where we found it, the name of the safe function, and eventually the count of the hits that it would have in one specific Windows library function. It was really just that simple. We just counted and put everything into the database that you see designed down here. I'm going to talk about a little bit more shortly. In there, we collected all the hits of safe functions, which we defined as signatures in Windows libraries. And later on, we'll do nothing else than use the same Python application I mentioned up there for producing diffings. The output is actually in a CSV format, so we could very well just put it back into a database. And later on, as a future approach, add more Windows versions to our diffing approach to diff between more versions than 2. So, as mentioned, we would get the C representation, the decompilation, by using either Pro, and eventually end up with all the source code of the Windows libraries, which we then put into our parsing application, which is an open source Python project released on my GitHub profile that can take all the C representations, put them in a database, and eventually produce a diff. And as you will see later, we now even have a GUI for usage of this application, which makes me especially proud. More about this soon. So this would manage all our libraries and functions and the signature hits and allow us to do diffings. This again is the database design. So we focused clearly on the hits. It's really simple. You could very easily extend it, but this is actually all you need for following the approach that we had. We have representation of the libraries and all their functions, and eventually all the hits of safe functions that we found in these functions. And finally, we're at the diffing. This is an example how our diffings look like. So really just very simply counting the safe functions in the dedicated functions of the libraries and check if we find any differences in there. Very much text, this would be how you could configure our tool. This is actually the most accurate documentation that there is so far, so memorize it well. These are the command line statements that you could need if you want to use it on the command line, and there's even more command line statements back here. But what I actually wanted to show you was the GUI. I'm very, very proud of the color scheme. Don't laugh now. This actually follows rules. I admit I was too lazy to implement multi-threading in that application at the moment I wrote it, so I just put everything into one GUI, one interface, and this is all the functionality that there is. and I just divided it by 5 boxes that we have on there, and I used the colors so I could actually say, all right now, in the yellow box there is all the configuration you have to put. You have to connect to some database, and you have to configure the interface of the database. So if you want to connect to Microsoft SQL, for example, you need to put access credentials, right? So this you can do in the configuration dialog. All right, of the functionality, most importantly, the blue box. There you can do the generation of the C files, which actually changed a little bit, I see right now. Never mind, I'm going to show you the GUI pretty soon, live, how it works. In the pink part, you can do the parsing of the C files. You can switch between Windows 7 and Windows 8. And in the former version, we had LST still implemented for people who don't have the Hexrace plugin, like me, for example, can parse the LST files. But if, as you might know, like the decompiled version of C file is like C code, and the LST stuff is like assembly, which by definition is like 4 to 5 times bigger than the C code. So as our tool, which is not the fastest yet, is quite really slow on C files, it will take forever to use it on LST files for all the Windows libraries. So that's why we canceled that functionality. And the fourth and most important part is the diffing, where you can produce CSV file format diffings for the Windows libraries. All right, so much to the theory and to the future. And now we're going to show you how the tool actually works. I hope. All right, too small. Okay, so this is the most beautiful GUI ever seen on this planet. Cool. So, and I actually want to say in the beginning we tweaked a little bit because the parsing takes really long. We did that already and filled our database before the demo. Anyway, now I will show you how, for example, you could generate an IDB in the C file, because this is actually pretty beautiful, as you see all the windows of either Pro popping up and closing down again. So in the first place, you have to define the directory of either Pro and which DLL or sys files you actually want to parse. We have very simple here. Now I'm going to go on and parse Windows 7 system files. But there should be colorful windows popping up now if this works. No? Oh. All right. Silently created. Now we have the IDB generated of our Windows 7 system files, and now we can generate C files where we need either Pro again. There we have the either Pro directory, and now we should have in there the IDBs of the Windows 7 sys files that we provided for the demo. And now we see how our tool instruments either Pro to decompile the IDB files that we produced before. So after this process, we should have ready-made Windows 7 source code in the demo directory in the .c format, so it should be valid C code, or more or less valid, as Hexrace doesn't always work right, which we could use later on for parsing. We will start the parsing engine and check for the 130 signatures that we defined in our database. As I can maybe show you now in the meanwhile, no I can't because the GUI is frozen. Actually here would be the configuration dialog where you can, oh it's back, where you can see the signatures that we have in the database and actually modify them. So if you find any other function you would find interesting for security research or for vulnerability research, you could insert it in here and have the tool search for it as well. Or even define more intelligent signatures than just these strings for having more profit. All right, now as the tool is finished, we should have C files in our directory. We can check in there if I find it. That's the wrong side. Oh yeah, so here's all the stuff that the tool produced, and we see in there is C source code and another C source code. So we used two libraries for the demo, and actually this is how it would look if we clean up the directory now. We would have these two libraries in their C code representation as a hex arrays output. All right, now what we would do is start the parsing. So I would insert the path of my C files in here and start the application in the background to do the parsing for Windows 7 and Windows 8 to have database output, which we're not going to do now because it takes hours. No, I'm actually kidding. It's not taking hours. It just takes like 20 minutes, which is too much for now. But if we finally did this, we have a database with a lot of hits, right? So we could start searching the database for our compiled library, which in our case was once ksec.dd and mrx.smb10, which we now have in the database. You can search here in this dialog and see we have these two libraries with IDs 1 and 3. So now I could go on and start the diffing on these libraries, which means I insert the library IDs here, press diff it, and this is the output. This is actually a pretty boring output, I admit, because there's just only one result in there, but actually a pretty cool result that Moti is now going to show you how you could use this to spot a potential vulnerability.
So basically, you may ask your question, why there is a difference? If Microsoft added a save function in Windows 8, why it's not exist in Windows 7? They already added. The answer for this one is simple. It's money. The Microsoft don't want to waste development time on all the operation system. And no one knows about these issues, just them. And they want people to move to higher operation system. So that's the reason that it still exists in Windows 7 and not 8. And about this project, what was the goal of this project anyway? How you can define if it's useless or not? If we get 1 0 day from this project, it's worth it. Now I'm going to say some example about the result.
Just 1 second. Keep talking.
OK. So basically, yes, this is a possibility. We found 1 good 0 days remotely. Now, when you diff, you have to choose. What are you going to diff? Userland modules or kernel modules? We started with userland modules, but we knew that there is no big chance we find something there. In the kernel, there was much more possibilities. Because if you get something, you can get escalation privilege. So in this research, we show some example in the kernel, diffing, and in the userland. By the way, I did not design the GUI. I hate to say that.
That's surprising again. Yeah, we had a huge discussion about the color scheme of the GUI, but I didn't see any use in not making it colorful, so it's chewing on design. So right now I'm just generating the IDB files for the Windows 8 drivers, as I didn't do this before, for being able to opening them up in either Pro and show you the actual missing security functions, which should be finished pretty soon, I hope. And afterwards, we're going to show you some results that we found with our diffing of missing security patches. Works. Nice. So now we should have IDB files of the diffing that I showed you before. I'll show you again. This was the ksec.dd sys driver, and there should be a potential vulnerability in the SSPI copy auth identity function, which is indicated by missing ulong add functions. And if I'm right, we have IDBs in there? No.
That's okay.
Good thing. How do I close the IDB?
I will try.
Awesome.
OK, so basically, the result. As you can see, we took all the modules of Windows, and it gave us a lot of files. As you can see, all of them, it's text files, and each text file will tell you, just open one for example. Each one will tell you, okay, this function appear one time in Windows 7, 0 time in hits, so 1, 2, 3, 4, 5, 6, and again here, and again here. So basically now your job is basically to go 1, 1, 1 and check which one is relative and which one is not exploitable. So just take a quick look, most top result. It's like here, example, CNG. You can see here in this function, convert RSA private. In Windows 8, this function appear 8 times. In Windows 7, 4 times. So first you want to verify that this is the case. So you take this file. This actually, in this case, it's a driver, CNG. So first thing you want to know if this driver is loaded in the system. So you just can use simple driver view. And CNG, you can see it here. So you see it's something about the cryptography of Windows. So this driver is loaded. Now you're just going to go and open the first version of Windows 7 and 8. Go to this function and see if there is a difference. So let's do that. Let's open here. Files. CNG. So this is 7 version. That's the symbol. Yes. Open another one. The Windows version, the Windows 8 version of the same driver. That's okay. It's already open. And now we're going to take the function. It's very simple. Just do a search text. It's already open actually. Mouse dead. So this is in Windows 8. You can see 1, 2, 3, 4, 5, 6, 7, 8 times this function was added. And if you open the same thing in Windows 7, you can see it's only 1, 2, 3, 4, and downstairs there is no any more continue of this save function, so something is possibly wrong. If it's exploitable or not, now it's another issue. Basically what you do is basically try to figure out who called this function. In this case, it's export full RSA key. So you go up and go again. So this is bcrypt export key. And you go up again and again, until you get, okay, bcrypt export key. It's probably an export function somewhere here. So now your job is to figure out how the system called this function, and if you can get to it from a userland, then you get escalation privilege. This case, I don't know if it's exploitable or not. I know that there is other case that actually exploitable, even remotely. And now we're going to show some other example from userland. So example here, this is a DLL modules. You can see this bcrypt. That's the function name. Here you can see in Windows 7 it was added few checks, and Windows 8 didn't. Again, this is a bcrypt DLL. Net login.dll in Windows 8. You can see a lot of RTL unlong add. Save function was added to this add research group to some info. And Windows 7, no such function exists. If it's exploitable or not, we don't know yet. But at this point, it's not. Again, another DLL, TW extension. You can see unsigned long to unsigned long after strlen check. And in Windows 7, you can see that basically no check has been done. And again, after this userland, we move a little about checking what happened in drivers. And we can see this CNG, the cryptography driver. you can see that there is few checks in Windows 8, but none in Windows 7. And another one is this copy auto-identify. In Windows 8, Microsoft actually added a security check, while in Windows 7, they didn't. So the entire idea is basically to figure out how to trigger from a userland to these drivers and get the escalation privilege. And again, so there is a lot of results that actually give us all this stuff. But I can tell you that not 99% of them probably not exploitable, but 1% is exploitable, for sure. And here another one. This is a userland. You can see this function, crypt decode object, strlen, mem copy it directly. And here, just make sure that the length is not too big. I will explain a little about how you figure out how to trigger it. This case is crypt DLG. So basically, it's some dialog box that do some encryption, show you some encryption stuff. And the function is decode. What is decoding? Some sort of an attribute. So you just Google here and there and tell you about what is this crypt DLL function. You should do it like for every module or something. So it's basically show you some stuff about the certificate. This is the function name, crypt decode object API. So basically, you just need to research the entire function to figure out if you can reach it or not. And this is example, the certificate dialog that actually connect to this function. So it shows you the certificate information. So if you put a very long string in a certificate, it's possible you will trigger heap overflow or something like that. So that's the idea, that you have to figure out what is the trigger point. So the entire research was basically just to find the issues. How to trigger them is another issue. So what next?
All right, closing our talk, I want to tell you some things that we plan to implement in the future. We actually try to extend our tool to diff more than just Windows 7 and Windows 8. We know there is now Windows 8.1 out there, and we could very simply add this to our data set and create something that's maybe not big data, but medium-sized data, and try to figure out if there's vulnerabilities in Windows 8 that we could target. We could very easily extend our signatures to have more intelligent signatures than just the strings of the save functions, to maybe even add some intelligence to evaluate the potential vulnerability that we're spotting by searching for a possibility to trace the input values of a function that we identify as potentially vulnerability, or ideas like that. I also heard symbolic execution would be an interesting thing to add to our application. I'm not sure yet if this is actually implementable in the form we have it now, but we will definitely put some research on that. And what I actually want to do myself is provide a transparent database library, because right now we depend on Microsoft SQL and SQLite, where Microsoft SQL is not available for everyone, and SQLite is really, really slow. We try to find a way somewhere in the middle, which might be Postgres. And we have a lot of known issues. As we mentioned, we have a lot of false positives, like really a lot of false positives, and a lot of duplicate hits that we could tweak with the signatures. And yeah, we're really, really slow in diffing. But we're automated, so it's not really us who are slow, but the tool, which can work on its own, gladly. And the output is in a CSV format. It's not that handy yet to handle. Like, I would love to put more information in the output that we actually generate to be able to evaluate the potential vulnerabilities better. All right, well, that's basically it with our talk. I hope you found it interesting, and if there's any questions, we're happy to answer them now.